Section 3.6 involves one of the most important rules that you will get this entire year. It's called the chain rule. There's a little bit of a quick review to all this. The chain rule involves composition of functions. I'm not going to go through all this for time on the video, but you could pause it and take a look at a couple of these. I did a couple examples for number 1 and number 2, just with these functions f, g, and h. Take a look at it and just kind of review and remember about the composition of functions. I didn't do all of those there. When you have any questions, you can ask me about them. And this one's kind of a fun one too, because you have to go backwards where we give you the composition functions and you got to figure out what it's the composition of. And that's a nice little challenge there as well. But I'm going to go ahead and get into the nuts and bolts of what we're going to be doing. And here's an example that why we're going to need the chain rule. We have y equals the cosine of x plus tangent of x, and they want the second derivative. So the first derivative is no problem. It's negative sine of x plus secant squared of x. And remember, secant squared x actually means the secant of x quantity squared, secant x times secant x. So the question is how are we going to deal with the composition of these functions? The function being, we have a function, the squaring function, where we're squaring something, and then we have the secant of x. So there's a kind of a function inside of a function. That's a composition of functions. So we have f of x equals x squared, which is the squaring function. So we have g of x equals the secant of x. So what we have here is an f of g of x equals the secant of x squared. So how are we going to be able to figure out how to do that? Well, it's going to be with the chain rule. So let's talk about how that happens. And here's the chain rule. And this is going to be kind of an interesting way to start with it. Hopefully you've already watched the video of the cartoon guy. That's a really good video. All of you need to watch it. The A group watched it Wednesday in class, and I'll probably have the B group watch it Thursday, but y'all need to make sure you watch that. But here we have y equals 6x minus 10, and they say that that equals, of course, if you factor a 2 out, 2 times 3x minus 5. And that's going to be the composition of the functions y equals 2 times u, where u is 3x minus 5. So this is 2 times u, which is 3x minus 5. And so y does equal 2 times u, where u is 3x minus 5. So we have y equals 6x minus 10. We have y equals 2u, and we have u equals 3x minus 5. So we have all those three equations that are related. How are the derivatives related? Let's take a look. dy dx, of course, is just 6. dy du, that's the derivative with respect to u, and of course that's just going to be 2. And over here, the derivative of u with respect to x, of course, is just 3. Now, if you take a look at this, dy dx should equal dy du times du dx. And of course, you can see here that the du's would cancel if you were multiplying these fractions together, and you'd be left with dy over dx. So it seems to work, doesn't it? And we know that dy dx is 6. We know dy du is 2, and du dx is 3, and 6, of course, is equal to 2 times 3. This notation right here is very important. It's called Leibniz notation, and we'll talk more about that as we go on, but it is super important, and we'll be using it a lot, and it helps solve a lot of tough problems that are AP test type problems down the road. Here's another example. We're going to relate some derivatives. The polynomial y equals 9x to the fourth plus 6x squared plus 1 can be factored into 3x squared plus 1 quantity squared. Of course, that's a composition of a function y equals u squared, where u is 3x squared plus 1 on the inside. So again, if we calculate those derivatives, we have dy du and we have du dx. We can take here on this function du dx, and here we have y, we can take dy du. dy du, of course, is 2u, and du dx would be 6x. So we have 2u times 6x. But we know that u is equal to 3x squared plus 1. So we can substitute in 3x squared plus 1 for the u. And if we do that, we get 12x, or 3x squared plus 1 here times the 2 gives me the 6x times 2 is 12x. 12x times then the 3x squared plus 1. 6x times 2 is 12x. Then distribute that 12x and you get 36x cubed plus 12x. All right, that's one way of looking at it. Let's just take the original polynomial. We have 9x to the fourth plus 6x squared plus 1. The real simple power rule gives us 36x squared plus 12x. 36x cubed plus 12x, excuse me. And you can see they're equal. So we can see that dy dx, again, equals dy du times du dx. du's are canceling. dy dx equals dy dx. So that's a cool example there. And this is just telling us what we're learning about. I'm not sure why that's clear back at this slide, but let's just move on. Well, I do want to say that, again, we're learning about derivatives of composite functions. You're going to learn what's called the outside-in rule and how to do a chain rule with more than just 2 links on the chain, repeated use of it. And we're going to learn how to do the slopes of parametrized curves and the power chain rule. So let's first of all get to the chain rule. If f is differentiable at a point u equals g of x, and g is also differentiable at x, then the composite function f of g of x is differentiable at x, and the derivative of the composition is equal to the derivative of f prime of g of x times g prime of x, which really basically means it's the derivative of the outside function with leaving the middle function alone times the derivative of the inside function. Leibniz notation, which I already mentioned, we have y equals f of u. U is some function of x like g of x. So it's just a different way of saying it. Y equals f of u. U is some function g of x. So then dy dx is equal to dy du times du dx. And where dy du is evaluated at u equals g of x. So let's take a look. S of t equals a sine of 5t minus 3. That's a composite function. We have s equals the sine of some u. In this case, u is 5t minus 3. So again, we have a complicated function inside of here. It's not plain old x or plain old t. It's some function in terms of t. So what does ds dt equal? Well, it equals ds du times du dt. So ds, if s is equal to the sine of some function u, then ds dt, so now we're taking the derivative in terms of t with respect to t, but there's no t here, it's u. So u is a function of t, so that's going to be the cosine of u, and then times du dt. And the cosine of u is the derivative of s with respect to u. So ds dt equals ds du times du dt. And again, you can see that the du's would cancel here, and you would be left ds dt equals ds dt. So let's take a look. If ds dt equals ds du times du dt, then that means ds du is going to be the cosine of u, and du dt is going to be simply a 5. So it's 5 times the cosine of u, but we know that u is 5t minus 3, so we can substitute a 5t minus 3 in there and get that. That's probably not the way that we will end up doing that. So here's the way you're probably going to be doing this problem. However, the reason I showed you this, even though it's a little more complicated over here, it is very important that you understand it. Now, you're probably going to have trouble with this right at first, so don't worry, but you'll get it eventually. This right here, though, is how you'll learn to do the chain rule, and it's pretty easy. It goes along with that video I told you about. So the sine function here is considered the outer function. So when I'm trying to take the derivative of, I got s of t equal to the sine of 5t minus 3. Okay, we know that the derivative of the sine of x is simply cosine of x, or the sine of t would be the cosine of t. But what we have in here is not just plain old simple t, but we have a more complicated function. And so we have a function inside of a function. It's a composition of functions. Now the outer function is clearly the sine of t or x or whatever you want to say. The inner function is, of course, 5t minus 3. All right? And a lot of times we say the outer function is the sine of u. This is what we said right up here. Sine of u is the outer function. 5t minus 3 is the inner function. It doesn't really matter. I guess you need two different variables, so that's why they use u. So s equals the sine of 5t minus 3. ds dt is simply going to be the derivative of the outer function, which is the derivative of sine is cosine. And you leave the inner function alone. Don't touch it. It's simply the outer function is the sine of something. The derivative of the sine of something is the cosine of something. Then times the chain rule, which means you take the derivative of the inner function, 5t minus 3, and that derivative is 5. And so my final answer is going to be 5 times the cosine of 5t minus 3. And all we did was slide the 5 that was at the end and just put it in the front. No big deal. So you take the derivative of the outer function, leaving the inner function alone, times the derivative of the inner function. That's the chain rule. I think that their video does it really, really well. I really, again, make sure you watch it. Sometimes it helps to think of the chain rule this way. We got if y equals f of g of x, then dy dx equals f prime of g of x times g prime of x. Again, the derivative of the outer function, which is f prime, leaving the inner function g of x alone, and then times the derivative of the inner function g of x. So here, in this example, we have the cosine of 3x to the fourth minus 2. We're taking that derivative. The outer function, of course, is cosine. And the inner function, the cosine of u, and the inner function is going to be 3x to the fourth minus 2. That's what's on the inside. So in other words, we're letting u equal 3x to the fourth minus 2. So we know that the derivative of, with respect to u, of the cosine of u is going to be a negative sine of u, but then the chain rule says we got to take the derivative of u with respect. Well, I'm sorry. Gosh, dang it. My bad. I didn't look at that closely. This is the derivative of cosine of u, and we're taking the derivative with respect to u. And since that variable is u, the answer is just negative sine of u. But if we take the derivative with respect to x of the cosine of 3x to the fourth minus 2, now what's on the inside is not plain old x. Here it was just plain old u, so we're good. But here we have a complicated inner function. So we take the derivative of the outer function, which is going to be, the derivative of cosine is negative sine, leaving the inner function alone, 3x to the fourth minus 2, times the derivative of the inner function, which is going to be 12x squared. 12x cubed, you can't see. And so 12x cubed, we just put it in front with the negative sign, so it's negative 12x cubed times the sine of 3x to the fourth minus 2. We could have also done, if we said that y equaled the cosine of u, and we said that u equaled 3x to the fourth minus 2, we could say dy du is negative sine of u, du dx is equal to 12x cubed. And then we also know then that dy dx is going to be dy du times du dx. And of course, that is going to be equal to negative sine of u times 12x cubed. But we know that u is equal to what? We know that u is equal to 3x to the fourth minus 2 times 12x cubed. And of course, that's the same thing we had before. So that's the Leibniz notation that you can use with the chain rule. We don't normally, like I said, we don't normally do that. So you're basically going to do it the simple way. Most 99 times out of 100, you're just going to take the derivative of the outer function, leaving the inner function alone, times the derivative of the inner function. Let's take a look at another example. With a motion, an object moves along the x-axis, so its position at any time t greater than 0 equal to 0 is given by x of t equals cosine of t squared plus 1. Find the velocity of the object as a function of t. So the velocity, of course, is the derivative. The outer function is cosine, so it's going to be negative sine of leaving the inner function alone, t squared plus 1. The derivative of the inner function, t squared plus 1, is equal to 2t. So there's your chain rule. So that's going to be negative 2t sine of t squared plus 1. And that's all we were asked to do is find the velocity as a function of t. So we're done. A lot of similar examples. I think hopefully you're catching on. Differentiate sine of x squared plus x with respect to x. Y is the sine of x squared plus x. Again, the derivative of the outer function, dy dx, is the cosine of x squared plus x, leave it alone, don't change it, times the derivative of the inner function, which is going to be 2x plus 1. So you've got 2x plus 1 times the cosine of x squared plus x. Again, starting to hopefully get repetitive for you. But here now, we're going to get a little more complicated. We've got a repeated use of the chain rule. So now what we have is we have 3 links to the chain. So instead of a function inside of a function, we have 2 functions inside of a function. In other words, a function inside of a function inside of a function. So we basically have f of g of h of x or something like that. So when we look at this function right here, we see we have the most inner function is x squared. The sine is outside of the function x squared. And the third function is the cube root function, or raising it to the 1/3. So since the most outer function is something to the 1/3 power, we know that when we take the derivative of something to the 1/3 power, it becomes 1/3 times that something to the negative 2/3 power. That's the power rule. So now you go inside and take the derivative of sine of x squared. We left it alone, remember, on the first one. We leave it, outer function is to the 1/3 power, so it's 1/3 something to the negative 2/3. Now what's the sine of x squared? Well, you got another chain rule because you have x squared inside of the sine. So now the outer function of this is going to be sine. So the derivative of sine is cosine, leaving the inner function x squared alone. And then the derivative of x squared is 2x. And now every year I get kids saying, well, how do I know when to stop? How do I know when to stop? Well, of course you know when to stop when you get to the most inner function. There's no function inside of x squared. That's the simplest function you have. You have a simple x raised to the second power. So you stop. You don't go any further. You clean it up. 2x times the cosine of x squared. You got 1/3. You can take this to the bottom if you want and make it to the positive 2/3 power. The 2x cosine of x squared is on top. Then you got a 3 on the bottom along with the cube root of sine squared x squared. So again, that's a cube root, and then we're squaring the sine of x squared, so it's a sine squared x squared. So remember, the sine of x squared is the same thing as the sine squared of x. Okay, 3-link chain, same thing. We've got the most inner function here is 2t. We've got then the sine of that inner function, and then we got the tangent of all of this. So the tangent's the most outer function, So g prime of t is going to be the derivative of tangent is secant squared of something. We have the tangent of something, so the derivative is secant squared of something. That something is not plain old x, so we have to take the derivative of that. The derivative of 5 is 0. The derivative of negative sine is going to be negative cosine of, again, leaving the inner function 2t alone. That is the last chain link. There's nothing more, so the derivative of 2t is 2. You're done. And you clean it up. You got a negative sign, you got a 2. Bring it around front, negative 2, cosine of 2t, and then times the secant squared of 5 minus sine of 2t.